So up next is, it says, explain what this interval means. And that's what this is. That's part B. Explain what this interval means. First part of this is what's your interval? We calculated that. Second part is explain what this interval means, okay? And then the third part of this, it says, explain what 95% confidence means. And we haven't really talked about this. So what does it mean to be 90% confident? And here's what that entails. Here I have, I'm going to create 100 samples of size 10, okay? And what it's going to do is it's going to create, based on this sample value with a mean of 50 and a standard deviation of 10, okay? It's going to create a confidence interval, okay? And it's going to create two of them. It's going to create a 95% and a 99% confidence interval at the same time. So I'll just do it and I'll show you what happens, okay? So what I have here is the orangey part is the 95% confidence interval, and then the little blue wings on the end is the 99% confidence interval. And what this shows you is how many values, or how many of these confidence intervals, the mean of 50 actually sits in, okay? And what you see is it sits in the orange, it sits in the orange, it sits in the orange, and here, this one, it doesn't even hit this confidence interval at all, okay? And then this one here, it hits the blue, which means it's in the 99% confidence interval, but not the 95% confidence interval. And it misses this one. 99, 99, 99, miss, 99. So what you have here is you have, for the 99% confidence interval, 97% hit and 3 did not hit. Okay, for the 95% confidence interval, 92 hit and 8 hit. So if I do it again, am I going to get the same results? The answer is no. Here I had I had one miss on the 99% confidence interval, it looks like, and then I had 2 not misses. This is 4, and I don't know where they're getting that because I must be blind and not seeing it or something. But it looks like 1 didn't hit here. Okay, so as you can see that you could have a confidence interval not hit the true value. It's not going to hit every time. What it should do is it should hit, realistically, 90% of the time you should contain the true value, and that's what it means. But that's not what a 90% confidence interval means. What a 90% confidence interval means technically is this. If I were to take all possible samples of size n, okay, in our situation that was 1,000 for a problem. If I would take all different possible combinations of samples size 1,000, and there are, you know, ungodly numbers of them, that would be back into figuring out combinations and permutations, okay? If I take all possible samples of size 1,000, okay, then what that means is 90% of all those possible samples would contain the true population proportion, or means if we're talking about means. 90% of all those possible confidence intervals that I could build off of those samples would contain the true population value. So it's saying if I take all possible samples and build confidence intervals from them, 90% would contain the true population proportion. And if I change it from 90% to 95%, then 95% of those would contain it. Okay. So that's what a confidence interval means. Okay. Now D says this. Did I start this up again? I didn't. Poop. All right, now I got to go with 05. We're going to go with 5 minutes, okay? So then what D says is the company must decide whether to now do a mass mailing. The mailing won't be cost effective unless produce at least a 5% return. What does your confidence interval suggest? So based on this information, do we have at least a 5% return? And our answer is, well, our predictions are that our minimum value is going to be 10.6%. Do we have at least a 5%? The answer is yes. Why? Because we know that our value is above, or is way below here, okay? So, are we going to produce at least that? The answer is yes, we are. So we have to base we can look at our confidence interval and say, Does it make sense based off of this value? We need at least a 5% return? Yes, because 5% is below this. That makes perfect sense. All right, so here's the next thing I want to do. If I go back to our confidence interval, 0.123 plus or minus 1.645 times the square root of 0.123 times 0.877 over 1,000, okay? And I say that's a 90% confidence interval, okay? 90% confidence interval, and I want to make it a 95% confidence interval. So here's my 90% confidence interval right there. It goes from 0.106 to 0.14. And I want to change it to a 95% confidence interval. How do I do that? I'm not changing this. I'm not changing this. What I'm changing is this. And this is going from 1.645 to, instead, 1.96. So what's going to happen to this? Is it going to stay the same? Is it going to get bigger? Is it going to get smaller? And the answer is, it's going to get bigger, because this margin of error, this value here, I'm taking this exact same thing, multiplying it by a larger number, so the margin of error is going to be bigger. If the margin of error is bigger, what that means is that my confidence interval is going to be bigger. Okay? So, in a manner of speaking, I'm going to be more accurate, because I went from 90% confident to 95% confident, and I've increased that range. But what that also means is that I am at that point less precise. Because now, instead of saying, I'm pretty sure it's within this range, I'm saying it's pretty sure it's within this range. So I'm less precise as to where it could be. And that's a trade-off that you have. If you increase the confidence, you increase the size of the range, so you're not as precise, but you're more confident that it's going to be there. Okay, so far? Yeah, that's good, senor. I know, it is. All right, so last part of this I want to talk about. 0.123 plus or minus 1.645 times the square root 0.123 times 0.877 over 1,000. What happens if I double the size of the sample? Now, keep in mind that we know that the larger the sample, and as long as I'm meeting the criteria of being less than 10%, the larger the sample, we've always said, the more accurate you're going to be. Is that going to portray to here? So I'd have 0.123 plus or minus 1.645, same confidence, times the square root of 0.123, assuming that this is the same, 0.877 over 2,000. Okay? Now, let's find out what happens here. So let's grab the calculator, and we'll start off with the square root of 0.123 times 0.877 divided by 2.123, and I get a standard error of 0.002. So this is 0.002. This is still 1.645, and I'll multiply that by 1.645 times 1.645, and that's the same value, so that's not going to change it. But I get 0.0038, so this is 0.004. Okay, now my margin of error is 0.004, and this, my previous margin of error was, what was my previous margin of error? My previous, 0.017. So now I got to compare 0.017 to 0.017 to 0.004. All right. So my margin of error is smaller, and if I think about that, what that means is stop that. All right. What that means is that I went from a range like this, where I went 0.017 out in each direction, to 0.004. 0.004, it's going to be a much smaller range. So I'm becoming more precise. How much more precise am I? Realistically, how much more precise am I? And the answer is, well, if I think about how I multiplied this, because this value is in square root, I didn't become twice as much precise. Okay? So what I have to do is I'm going to take 0.017, 0.017. I'm going to divide it by 0.004, and I got 4.25. Okay, 4.25 is a rounded value here. Okay, but I didn't become twice as precise. I became 4 times as precise. And really, what's 4 times? It's this value squared. It's that doubling that I did, and because it's in the square root, it would be squared. That's just go with it. At that point, we're done. We'll have more problems in class.